Professor Barry Sanders is an AITF iCORE Strategic Chair in Quantum Information Science at the University of Calgary. He also holds the QianRen B Chair in Quantum Information at the University of Science and Technology, China. Professor Barry Sanders has a wide range of interests, right from the fundamentals of quantum information to more applied areas such as quantum optics, quantum computing, and quantum metrology. Professor Sanders, good to have you with us.
Thank you.
What is a quantum computer?
Well, a quantum computer is basically a computer, but it would operate differently than existing computers by making use of quantum physics. And quantum physics in the past has described only the way that atoms and molecules work. Nowadays, we're pushing the principles that govern atoms and molecules to larger scales, and by doing so, our new computers, our so-called quantum computers, should be able to solve certain problems efficiently that would never be solved without exploiting quantum physics.
So what are the characteristic traits of quantum mechanics? Are we living in a quantum world? Is this a classical world? Could you define what quantum mechanics really is all about?
Well, in principle, we live in a quantum world. All the laws of nature at a fundamental level are governed by quantum physics, but for all practical purposes, we can ignore quantum physics when we build a bridge, when we make a car, when we build the kind of things that we use on a day-to-day level. And quantum physics, although it applies to everything in the universe, is only necessary as a description at the atomic and molecular scale, except nowadays with new technologies, the ability to build new materials, to design tailored media for electron transport, for controlling light. Through these new technologies, we're able to push the laws of quantum physics to a grander scale, much beyond the molecular scale. So in the usual laws of nature that we consider, we follow the subjective principle. We think that every property of a system is measurable and well-defined at any given time. So if we think about the moon going around the Earth, we don't think it's puzzling to say, where is the moon and how fast it's going at the same time? In quantum mechanics, we have trade-offs in this kind of information. So a pair of questions, like where is the moon and how fast it's going, are not simultaneously answerable to an infinitely precise scale. So quantum physics tells us how these kinds of trade-offs occur, how the world is really uncertain or indeterministic at some level.
But doesn't that make the world very fuzzy, and our conception or perception about science is that it gives definite answers, it helps us predict the future, it helps us build machines, and that is the accuracy and precision that science harbors, that's all at stake. Doesn't this make the world very strange and a fuzzy place to live in?
Yeah, so it does make the world fuzzy at some small scale. So for all practical purposes, we're able to use science to make precise predictions. But at the fundamental level, this kind of fuzziness helps us. If it weren't fuzzy, the electron orbiting the nucleus would fall into the nucleus. All the atoms would die. So the idea that the electron position is a bit uncertain ensures that atoms behave the way that they do. In quantum computing, the fuzziness is also important because through that kind of fuzziness, we can prepare, instead of a string of zeros and ones that go into a computer and answer a question, instead we can prepare a superposition of all inputs. We can make this fuzziness work in our favor by essentially building parallelism into a computer on a single chip.
You talked about the moon, and you've said that you can't know at the same point in time where the moon exists and where it is headed to. So how in the world have we come up with these accurate predictions of astronomical events, when solar eclipses occur, when lunar eclipses occur? Where does Tycho Brahe's work stand? Where does Kepler's work stand? We have quite an astounding, accurate prediction of astronomical events. So where does quantum mechanics play its role here?
In the astronomical scale, where sizes are very large, distances are large, quantum mechanics plays no role in those. Quantum mechanics has a scale to it. So there's a constant. It's known as Planck's constant, named after Max Planck, who was father of quantum mechanics. And that gives us a scale for which quantum effects become important, and those effects are down below nanoscale, below nanometers. So if we're trying to predict things, how objects will move on a, say, the scale of a meter or a light year, then we can ignore the quantum effects in that. Quantum effects do play a role in stellar phenomena. For example, if we want to understand how stars work and how they collapse, quantum effects do come into play, but not for the kind of stuff that Tycho Brahe and other astronomers worked on.
So quantum mechanics, it seems, plays a major role, or its manifestations are clearer at the nanoscale when you go down to the atoms of photons, molecules, or ions. But you talk about quantum computers all the time. The computers that we deal with today are laptops or palm tops. Clearly, they're not at the nanoscale. They are big devices, and these are the devices we would normally like to work with. So how would a quantum computer work? How would we access a quantum computer if it's so small?
Well, first I'll mention that even the computers of today, although they don't operate on quantum computing principles, they have quantumness in them. They have transistors. Transistors involve electron tunneling, so electrons can pass through forbidden regions, and that's only allowed quantum mechanically. So even today's classical computers do have components that work on the nanoscale, and those are sub-nanoscale sizes. A quantum computer would be a lot more challenging because we have to do more than just make an electron tunnel. So in those systems, we would have each bit would be represented by some object. It could be an ion, which is a charged atom, whose electron orbiting it can have different energy levels that can represent the 0, 1. We might trap these ions in an electric field and hold them there. They would serve as a string of bits. Or we can make use of superconductors or cold atoms or photons, which are particles of light. The trick is that we have to get quite a few of these things to behave very well, to stand still or move in a directed way, and we have to be able to write onto them and read from them. And yeah, these are big challenges. The questions you're asking relating to the scale and quantum mechanics breaking down, we have to kind of fight nature on it. We have to make quantum mechanics work on a scale that normally we think it doesn't. It's an engineering challenge.
All right, so it seems that a quantum computer would involve microscopic objects to be controlled and engineered in a very precise fashion. But how would a normal human being, given the level of scientific literacy that we have all around the world, would be able to harness such an ionic computer or such a molecular computer? I can't expect my sibling to operate a trap of ions or a bunch of photons beaming on a chip. How would these quantum computers promise to replace or supplant the classical computers we have? Aren't these classical computers good enough?
Well, so classical computers are good enough for almost everything that we want to do. But there are certain problems which can seem somewhat esoteric. For example, factorizing numbers or simulating quantum dynamics to develop new materials. These kinds of things the person doesn't need to use on a day-to-day level, but they're critical for everything from national security to developing new technologies, or they could become critical. What we expect would be that we wouldn't have quantum computers on everybody's desk. We wouldn't carry them around like laptops. But nowadays, we're moving towards the cloud. And with the cloud, we can imagine having a quantum computer in a well-controlled lab, and then it interfaces. So the architecture becomes a little bit challenging. If you wanted to use the quantum computer and it were sitting in my lab, you might interface through the internet, and your program would execute instructions that would cause certain things to happen in my lab. So you might have an algorithm that runs, that executes an instruction, that turns on a laser beam, or it might modify an electric field. So my vision of where quantum computers will go is that people will have access to them, but through a cloud where the quantum computer operates under very controlled conditions, very cold temperatures, high vacuum, and so on.
So how long would that take?
Well, it's hard to predict the future. And the time scale to make a working quantum computer that would be able to answer problems that are outside of the reach of today's problems could be on the scale of decades. So it could take a long time, but we don't know. I'm often very pessimistic about these things, so I'm pleasantly surprised by breakthroughs quite often. If there are some good breakthroughs in technologies, in materials, and also in quantum coding strategies, algorithms, and so on, we could see a quantum computer solving interesting problems earlier.
What do you mean by interesting problems? Are there problems that our conventional computers find too formidable to attack and which quantum computers promise to solve with greater facility?
What I call an interesting problem is a problem that will forever be hard on a classical computer. So at the moment, the most efforts on computers are to make existing computers better and better. We make them smaller, we make them faster. But the kinds of problems that are solved on the computer don't change. So we might integrate differential equations, or we might solve some linear equations, or find various problems, and then if we make the computer better and faster, it can solve larger instances of those kinds of problems. But other kinds of problems, such as factorizing, we don't expect ever to be solvable efficiently on a regular computer. In fact, those assumptions are crucial for beliefs about security on the internet. So if you put your credit card number on the internet, you trust it won't be broken because you believe it's always going to be a hard problem. To me, the quantum computer is interesting because it will take problems that we believe are hard and actually make them easy to solve. That's what's interesting.
All right, so there's a great push in science these days to mimic biological systems. And you've also talked about that inherently, at the fundamental level, there's some quantumness to our existence. This world operates quantumly, though we don't see these effects on the macroscopic time scales or size scales that we generally operate. But are there any examples of quantum effects happening at the biological scale?
Well, so you've touched on a very hot area at the moment. We think of this as quantum-inspired biology research. So this kind of speculation has been going on for decades. It started, as far as I know, with Erwin Schrödinger when he asked the question, what is life, and wondered about DNA mutation. Well, not DNA, but he wondered about mutation and whether it was quantum-driven. Those early investigations suggested quantum effects weren't large. But nowadays, we're seeing some very interesting phenomena. For example, there's a bacteria that lives deep below the surface, and it has to make use of every photon, every particle of light it gets. It does photosynthesis, the same that any plant does, but it seems to make use of quantum coherence. It uses quantum transport properties to be able to get the maximum energy out of that photon. That is of practical interest for research on solar energy and batteries. Also, there's work on compasses, magnetic compasses. A lot of animals can find which way is north or south, but there's a bird that can find the north-south axis but not know which is the north-south direction. And that suggests that entanglement, which is the famous basic mystery of quantum mechanics, seems to play a key role in the chemistry of that bird's receptor. And there's other speculation that is finding solid ground, such as the sense of smell. And it seems that there are quantum effects related to hydrogen bonds that enable our ability to smell things have much more versatility than is suggested by non-quantum. So we are starting to find interesting quantum effects in biological systems.
I would like to ask whether these processes that are found in biological systems, navigation on a magnetic landscape or sniffing, would these qualify these systems as quantum computers? Because you've used the word quantum-inspired systems. Is there any difference between both of these?
As I said, these are quantum-inspired. So as we do quantum computing and we start to realize that entanglement is some sort of a resource that we can do quantum computing, coherence is another kind of resource, we're discovering that these effects could be manifested in biological systems. They could be important for life itself. But these are not behaving like a quantum computer. So far, we don't know any evidence that life forms behave like computers, whether quantum or not quantum. But there's always that possibility. The way the brain works, the way that thought works are great mysteries to us, so we never know what we're going to find.
You've talked about entanglement. Could you shed some more light on entanglement?
Well, so I mentioned...
Sorry, it adds to the mystique of quantum mechanics.
Right. So the essence of quantum mechanics is what's known as complementarity. It's the trade-off I mentioned earlier, that you can't simultaneously describe where something is and how fast it's going. That captures all the inherent mysteries of quantum mechanics, but it somehow makes sense in an uncertainty principle. If we then ask questions about two particles, we say, instead of just the moon, let's say we talk about the moon and the sun, where they are and how fast they're going, they could be correlated in some way. So once we get to two or more particles and their common state, then we run into much more interesting mysteries. And this is what entanglement's about. That if we describe our world statistically, we say there's inherent uncertainty, then we can come up with limits to how precisely we can measure things, how precisely we can determine what the future is going to be. But if we have entanglement, we can have a super strong correlation that violates any attempt to describe things statistically. And so entanglement, Schrödinger described it as the mystery of quantum mechanics. Einstein described it as spooky action at a distance. So things get weird once we start thinking of entanglement.
Has entanglement ever been witnessed or seen in the laboratory?
Well, entanglement is seen regularly. When we do our experiments, when we look at two or more objects together, we've seen it. These kinds of things have been tested. What's interesting is there have been proposals inspired by Einstein's questioning of the completeness of quantum mechanics, and these are tests of so-called non-locality. And in the past few months, there have been 3 experiments that have not only demonstrated entanglement, but demonstrated that no reasonable alternative explanation can exist. So we're now so solidly on the ground of prove entanglement so well we can rule out any reasonable alternative. So the mystery is here to stay.
All right. So you've talked about different things when you were defining quantumness. You've now talked about entanglement. You've talked about parallelism, coherence. Is there complementarity, uncertainty, indeterminateness, your imprecision in measurement, your incapability to measure with a high level of precision? Is there a single characteristic that defines quantumness, or is just the agglomeration of all of these traits?
Well, quantum mechanics on a phenomenological level exhibits all these properties, but fundamentally it's actually a very neat and tidy theory. It's expressed in terms of mathematical axioms. So once we say things like every system state, all its properties are described by some complex valued function. These are the rules for measurement. These are the rules for describing a state. These are the rules for preparing it. We're done. So on a mathematical level, there's a simple, unified description that gives all these results. So it's not a collection of phenomena. It's a mathematical principle. And then all these phenomena arise out of that description.
Well, there's a quest for, these days, for phenomena or events or physical processes that seem very esoteric to the commoner. For example, there's a search for Marcini primes. There's a search for extraterrestrial intelligence. There's the search for exoplanets. There's the search for the 9th planet in the solar system. All of these searches seem to be of no practical use for the commoner. Is quantum information processing or quantum computing, the craving to build a quantum computer, a scientific luxury of the same kind? Will it ever become of practical value to the common masses?
Well, as I mentioned earlier, quantum mechanics underpins every law of the universe. So I think the most compelling reason to spend time learning quantum mechanics and also quantum information is because the universe as we know it, its laws emerge out of quantum principles. So if we want to deeply understand our laws, the capabilities of extending it, the capabilities of answering any mysteries, we need to know the quantum mechanics for that. That said, and as you've articulated earlier, the use of quantum mechanics is limited by some scale. But on the other hand, our technologies are pushing quantum mechanics to larger and larger scales, and we should be able to exploit. So the regular person on the street can get a lot of benefits. In fact, it's already happening. Medical scans make use of superconductors that perform very sensitive magnetic measurements. So if a person goes to a hospital and undergoes scans of magnetic fields to determine health, to measure brain signals, to measure how the heart is behaving, they are making use of quantum technologies right there. The ability of quantum mechanics to enhance our metrological sensitivity, our ability to measure tiny fields, is going to become better and better. So we expect quantum mechanics to deliver better sensors which will enhance not just medicine, it could be in geology, in various areas for sensitive devices. We also make use of quantum mechanical systems, as I mentioned earlier, in the computer, in hearing aids. These are transistors. So the idea of electron tunneling becomes very important. These kinds of technologies could advance a lot. And quantum mechanics could manifest in communication technologies. So there are a lot of different benefits that can emerge if we can get the scale of quantum effects to go beyond sub-nanoscale up to centimeters or meters. We could start picturing new kinds of technologies, new materials. So it's worth the investment.
All right, so the anthropologist or the social scientist these days would direct our attention to global problems which humanity now faces. It seems that the wealth that is possessed by about 100 people on this planet, that's the same wealth as possessed by half of the world population. We have poverty all around us. We have this monster that we call climate change enshrouding us. We have national securities at stake. So don't you think that these quests for futuristic tools is somewhat of a luxury, especially for the developing world?
Well, I think that these tools that we develop, the enhanced capability and also cost, can benefit everybody. For example, cell phones. You know, a lot of cell phone development has emerged out of high-level technological results, and these aren't only used by the richest 100 persons in the world. You find cell phones in communities all over the world, poor communities. It's transformed the way we communicate. With respect to climate change, the technologies could result in better ways to clean up dirty oil, to do carbon capture, to limit the damage that we get from fossil fuels. We could wind up with better solar technologies. I mentioned that understanding better how this bacteria behaves deep below the surface to capture and use every photon, every particle of light it gets, is being studied now for solar batteries. If that kind of technology works, if we can get better batteries, we could have cleaner cars, we could make better use of solar power. So I think everybody stands to benefit from the investment, not just the richest people.
What excites you about quantum computers and quantum information?
Well, for me, the excitement about quantum computing and quantum information is that there's the world of information technology built on principles of computer science that were inherently built on the principles of classical physics. And so I love quantum physics, and I love the idea that there's this whole world of IT and its concept of limitations and capabilities that completely transform once you recognize that the building blocks obey quantum mechanics. So for me, the most exciting thing is revolutionizing the community that I work in, is revolutionizing the way that we think of information technology, of computers, of what makes a hard problem, of how much information we can send down a channel. These kinds of questions that were thought to be fully answered and understood have now been undone, and the community I'm in is rebuilding that whole state of knowledge. It's not often you can be part of a revolution.
Do you think we're in a same point in time, a juncture in time, as the late 19th century when Charles Babbage made his first ideas about computation? He made his first machine. And then it had to wait up till the 1950s when the transistor was invented for practical modern-day computers to evolve. Are we in a similar state of affairs as far as quantum computers are concerned, or are we way beyond that?
I would say on a scientific level, we're at that stage. The concepts of computing, the questions of computability, the nature of turning computers into universal computing machines or solving computational problems, we're definitely at that stage again, where we're rethinking that whole way of dealing with information processing and computing. On a technological level, in some way we are, because when you mentioned Babbage and there was the vacuum tube technology, et cetera, it wasn't clear that anything would work, or at least not work well beyond some scale. And then the latter half of the 20th century and the early part of this century led to a very rapid development in computers. We don't know what's going to happen next with quantum computing. So we're kind of at the early 20th century stage where we're developing the concepts, we're trying to develop the technology, and just like then, we don't know if it's going to work or what scale. So it's very exciting. I hope that we replicate the rapid advance that occurred with what we call classical computers, but it's very risky and there's a lot of technological barriers. So that makes it very exciting.
So when information technology was developing, there was Shannon and the likes of Shannon, Wiener, who actually came up with strong theoretical foundations to information technology. Are we awaiting a theoretical renaissance in quantum computing, or are we awaiting a technological revolution? What kind of breakthroughs are we expecting?
Well, so we're in the same kind of revolution that you mentioned. Shannon, of course, did extremely important work and changed the way that people thought about information down a channel. Since then, Halevo, a Russian mathematical physicist, developed something that we call the Halevo capacity, analogous to the Shannon capacity. So we're finding these kinds of parallels come along where these older concepts have been completely transformed in the face of quantum mechanics. So we're seeing the same kind of revolutionary scientific thinking. It's in a much shorter time frame because we have that classical information knowledge and we understand quantum mechanics, so it's a little bit less challenging in putting it together. But these kinds of revolutionary thinkings are taking place. These changes are happening.
Is there a breakthrough that you're anticipating, or you would really like to have a breakthrough, to see a breakthrough in your lives?
Well, on a theoretical level, what I'd really like to see are more problems that I defined as interesting earlier. So at the moment, we have a very small set of problems that are worth solving on a quantum computer because they're forever hard on a classical computer. The revolution would be to find more of these kinds of problems, the things that tell us that we really need a quantum computer. On the other side, we need to push harder towards what we call quantum control, the ability to change the state of a quantum system protected from the damage that the environment, that the universe does to it. And those kinds of technologies, the control technologies, are another revolution that we need to happen. People are trying now, but these are big barriers. So one is we need more reasons to build a quantum computer, more problems to solve. And the other is we need to make quantum mechanics work on a larger scale, protected from what the universe does to it.
So are these exciting times to be in the arena of quantum information, or there have been more exciting times that you've seen?
Well, we're in the midst of a very exciting time. It's been exciting, it is exciting, and it will continue to be exciting. And what makes it exciting for me as a scientist is that there are more problems to solve than people to solve them. And the problems aren't always that hard. In some areas of physics, problems can be very difficult to solve. They've been around for a long time, and a lot of very intelligent people are hammering away at them, and they resist breakthroughs. In the field I'm in, there are more problems than people to do it. The techniques aren't as difficult to use as in some other areas, but they are challenging. And so every morning I wake up, I have a set of problems I can do, and I can solve some of the time. And every year when we look back on it, we see breakthroughs in that year from the previous year. So there's a sense of inexorable progress taking place and a feeling that we individuals can make a difference.
What excites you about science in 2016?
Well, on the largest scale, the things that I would like to think about in my spare time when I'm not working on quantum computing, probably the biggest one for me is still quantum gravity. That the universe has, on the large scale, gravity that makes planets orbit stars, that governs galactic dynamics and so on. And that force, the force of gravity, is quite distinct from the other forces we know. Electromagnetic, that tells us how light, electricity, and magnetism behave, and the weak and strong forces that work on a nuclear scale. And those three we seem to have unified. The Higgs boson discovery was a crowning achievement, but unifying it with gravity is one of the biggest outstanding problems out there. Another one that I would be excited by is the brain, how the brain works, how thought is manifested, and with my computer science way of looking at it, tying the brain in with thinking about it as a system that controls the body, that's able to govern the chemical behavior, the muscles and nervous system, would be a very big challenge. And there are many other problems, but those are the two big ones I think about.
A famous scientist, Anton Zeilinger, once said that since people don't understand quantum mechanics fully, and neither do they understand consciousness fully, therefore the two must be related. So do quantum effects, may they have a major role to play in consciousness and human thought processes?
So this is a long-standing discussion amongst quantum physicists, not just Anton Zeilinger, but Wolfgang Pauli, who proposed the Pauli exclusion principle, talked about this. Roger Penrose writes about it in his book. So people do think a lot about consciousness, whether consciousness represents an emergence of classical behavior from quantum systems, and so on. From my own point of view, I really don't have a deep understanding of consciousness, so I don't know if quantum mechanics plays a role or not.
Do you ever stumble into interpretative difficulties of quantum mechanics? Do you ever would like to derive meaning out of quantum mechanics, or it's just an objective reality, a set of axioms that is at work?
So I think of it, I have my day job, and then I have at nights, I can be whoever I want to be. In my day job, I'm a shut up and calculate type person. There's this mechanism, the mathematics all works. I pretend that all instruments are classical, and then the whole universe is quantum except those instruments, and I can calculate and I can solve every problem. So the mathematics works fine, and I try not to think about the philosophy. At nighttime when I go home and I relax, then I start to think about these kinds of issues, the interpretive difficulties. Are there many worlds? Is there some boundary condition of the universe that's really responsible for this behavior? Are there some weird hidden variables? So these kinds of questions are very interesting. I think they're philosophical at the moment, and I'm a physicist, so as a physicist I just calculate.
While managing such an illustrious career in science and technology, you've traveled all around the world, and you're a great proponent of the idea of science without borders, and that science is a common heritage of mankind. While traveling all around the world, do you think that there's a demographic distribution to scientific cultures, or are all of us, all of humanity, on an equal footing as far as scientific culture is concerned?
So I think almost every person, and certainly you see this in children, are driven to understand science. Young children are always asking good scientific questions. This scientific way of thinking, or this desire to know, doesn't always survive to later in life or to the culture overall. So when I travel around the world, I meet people everywhere that are interested in science, and not just getting answers to questions, but would really like to try to answer questions. But having a scientific culture requires a lot more. It requires a good education system, it requires investment, it requires not just an academic environment, but an industrial environment. And we see pockets of great science. Even in highly developed countries, the scientific culture is concentrated in certain cities and in certain areas. And if you look at history, scientific strengths don't last in one particular place. You can see a time when the great science was done in Paris. Later, it moved to Germany. And so you can see that there's a migration of scientific strengths from place to place. So my conclusion is that scientific culture is very fragile, that most of us are born having interest in science at some level, but the ecosystem required to sustain it is very fragile and takes a lot of effort. And so it's rare that we find pockets of great strength where the fantastic developments are taking place, and a lot of infrastructure is needed for that to happen.
Could you envisage a migration of these pockets of science from the west to the east, or from the north to the south, or is this a meaningless question?
No, it's not a meaningless question, and I can picture it. So, as you mentioned when you introduced me, you mentioned I have a QianRen or 1,000 Talent chair in China. And for me, it's a great privilege to be serving part-time at the University of Science and Technology of China, which is one of the best universities in China for science. And so I enjoy working there part-time. I enjoy engaging in it. But one of the fascinating aspects I find is that China is at the moment investing and trying to develop into a scientific superpower. They don't say that or broadcast it or brag about it, but from the inside I see that happening. And so for me, where I like to think of myself as a student of history and a student of scientific history, I feel like I'm a witness to a migration taking place. I think that China is consciously trying to build up the capability of sustaining a full scientific ecosystem. And I think that it needs to be a conscious effort. You mentioned earlier about the Renaissance and the idea of inviting and sustaining scientific thinking, of encouraging it, of supporting it. You know, Galileo was able to do scientific investigation. He received money for practical work, such as developing telescopes, but he had the right environment where he could explore and discuss. So I think that there are ways to create a scientific culture anywhere. We just have to be aware of them and work on them.
You've been visiting Pakistan and you're a frequent traveler to Iran as well, and of course China. You've seen science evolve in these countries. What's your take on the scientific enterprise in our part of the world? What needs improvement? What are the major challenges?
So my impression in this region, this is my 5th time in Pakistan. I've been to India a few times, Iran quite a few times. And you know, I see commonalities in culture. I think there's a lot of beautiful cultural aspects in this region. And I see that there's a lot of scientific inquisitiveness, a desire to learn, a desire to solve problems. I also see that people from these 3 countries come to my country, Canada, to the United States, Europe, Australia, and so on, and do extremely well. So my view is that there's a huge potential here. There are a lot of smart people. There's a good basic education system. There's good family structure that encourages learning. But for various reasons, the productivity, the scientific output in these countries hasn't been particularly high. But I think this is really due to the recent history in the region, you know, conflicts, upheavals, colonialism, these kinds of problems have restricted. But I think with the right kind of investment, the people are smart, the capability is all here. It just takes some high-level thinking about what needs to be in place to make scientific discoveries and breakthroughs happen. That said, of course, there have been great things that emerged out of Pakistan. And Professor Abdus Salam was a student at Government College in Lahore and is one of the greatest physicists of all time. He trained Riazuddin, who was also here in Lahore. So you can see, even locally, the talent has existed and remarkable achievements have been made. So the capability is here.
You've mentioned colonization. Well, that's very interesting. At the one hand, there's one school of thought that believes that colonization brought its benefits and its fruit to the region. We have a huge infrastructure, a railway system, a giant irrigation network in our country, thanks to the colonizers. But has colonization taken its toll on scientific progress, technological progress?
Yeah, my feeling about what happened with colonization, certainly when the British were around, is they brought education systems in place, but it was more to train a civil service. A lot of the engineers were trained in Britain and sent out. So the idea of the education system brought in by colonizers was not to create an independent, self-sufficient society. It was to be able to train people to enable the colonizers to occupy and make the best use. They needed trains, they needed transportation, they needed bookkeepers. But the scientific aspects of these institutions were not strongly developed by colonizers. It wasn't in their best interest.
So what connects our region, we call it in the Indo-Pak subcontinent, to Africa or to South America? Is it that all of us were colonized, or is it that there's something in our cultures, in our thought processes that makes us less scientifically aware? Or is it the economics that is at the heart of this problem of scientific lack of productivity?
I think that there's a cultural aspect. So in the Indo-Pac subcontinent, in a lot of regions, people really have a desire to learn. It can be scientific, it can be learning poetry, it can be learning art, music, but there is a strong desire to learn. Some of the learning is in the scientific area. So that desire to learn is a very important component of building a scientific community.
In Pakistan specifically, if science were to take a positive leap, would it happen bottom down or top up? Would we look to the government for support, or should individuals inside universities, inside colleges make up their own efforts? How does science progress?
So I think there are a lot of aspects that have to come together. There needs to be government support initially to provide grants, to provide a subsidized education so that people can learn from great professors, and even if they can't afford to bear the full cost. But there have to be opportunities at the end. When a scientist goes through, they have to know at the end that there are opportunities in industry, there are opportunities in government, that scientific knowledge itself is valued. So a lot of people who wish to learn science need to know that they're not just satisfying their intellectual desire, but they have made a good career choice. So that's important. It's important that the region emphasizes developing technologies that make full use of frontier scientific knowledge. It's important to have benefactors. It's important to have conferences, workshops, summer schools, so that people who are interested in doing science at all levels, from high school students, say, to university professors, to the general public, have a discourse going on where they're able to share and think about these ideas. There have to be journals and ways to communicate. There has to be access to the internet. So there are a lot of different components, and I think they all have to come together for science to work.
Thank you very much for an illuminating discussion.
Thank you.